On September 15th, 2017, at 4:55 in the morning, Pacific time, a spacecraft the size of a school bus is falling into a planet at 113,000 kilometers an hour, and it is still transmitting. No spacecraft has ever sent data back from inside a gas giant's atmosphere. No mission has ever deliberately destroyed itself to protect two moons that might harbor life. This is not an ending. It is a final experiment, run once, that cannot ever be repeated. Stay with me, because what that spacecraft sent back in its last 90 seconds is still being argued over by scientists right now in 2026. If you're new here, this channel breaks down real space missions in plain language, no filler, so if that's useful to you, the subscribe button is right there. Let us go back to the beginning. The mission was called Cassini-Huygens, a joint effort between NASA, the European Space Agency, and the Italian Space Agency, and it launched from Cape Canaveral on October 15th, 1997. It took nearly 7 years to reach its destination, arriving in orbit around Saturn on June 30th, 2004. That 7-year cruise was not wasted time. By the time Cassini reached Saturn, mission planners had spent decades building a working model of how gas giants behave, based largely on what the two Voyager probes had glimpsed in brief flybys back in 1980 and 1981. Voyager's snapshots were extraordinary for their time, but they were exactly that. Snapshots, single fast passes, through a system that needed years of sustained observation to actually understand. Cassini was built to stay. Over the next 13 years, it circled Saturn more than 200 times, using gravity assists from the giant moon Titan to repeatedly reshape its own orbit, a technique that let one spacecraft, without refueling, visit an entire system's worth of moons, rings, and magnetic environments over more than a decade. Over those 13 years, Cassini didn't just take pictures. It carried a suite of a dozen scientific instruments, cameras, spectrometers, a radar system for peering through Titan's thick orange haze, a magnetometer, a dust analyzer, and a radio science package capable of detecting gravitational tugs down to fractions of a millimeter per second. It confirmed vast lakes of liquid methane and ethane on Titan's surface, making that moon the only place in the solar system besides Earth known to have standing liquid pooled on the ground. It found Enceladus venting plumes of water vapor and ice grains from fissures near its south pole, evidence of a hidden ocean sloshing beneath a shell of ice. None of this was expected when the mission was approved back in the 1980s. It was earned slowly, one orbit at a time, over a mission that ran nearly 3 times longer than its original plan called for. By early 2017, though, Cassini was running low on the hydrazine fuel it needed to control its own orientation and point its instruments. And here is where the mission's builders made a decision that says something about how seriously science takes its own responsibilities. 2 of Saturn's moons, Enceladus and Titan, had emerged as genuine candidates in the search for life elsewhere in the solar system. Enceladus, with its geysers of water ice erupting from a hidden subsurface ocean, Titan with its lakes of liquid methane and a thick, hazy atmosphere rich in organic chemistry. If Cassini were simply left to drift once its fuel ran out, there was a real, if small, chance it could eventually crash into one of those moons, carrying Earth microbes that might have survived sterilization decades earlier. Rather than risk contaminating the very worlds it had helped identify as promising, mission planners chose to send Cassini somewhere it could do no harm at all, straight into Saturn itself. This wasn't a failure of the mission. It was the mission's final, deliberate act of scientific caution, planned years in advance and executed on purpose. What made the plan remarkable wasn't just where Cassini was going, it was how it got there. Starting April 26, 2017, Cassini began a sequence of 22 orbits nobody had ever attempted with any spacecraft before, threading the narrow gap between Saturn's cloud tops and the inner edge of its rings, a region roughly 1,600 to 2,500 miles wide that had never been directly sampled. Mission engineers called it the grand finale, and it set up everything that followed, including a discovery, buried in the 9th of those 22 passes, that scientists still cannot fully explain. Here is the number that matters. On July 2, 2017, during Cassini's 15th close pass beneath the rings, its magnetometer returned a reading that should not have been possible according to nearly 40 years of accepted theory. Every magnetic field generated by a planet, Earth's included, is produced by a dynamo, a churning ocean of electrically conductive fluid deep in the planet's interior. In Saturn's case, a layer of liquid metallic hydrogen thousands of kilometers down. And for that dynamo to keep working over billions of years, the physics demanded one specific thing: a measurable tilt, some real angle of difference between the planet's spin axis and the axis of its magnetic field. Without that tilt, the theory said, the electrical currents sustaining the field should gradually cancel themselves out and the field should decay away entirely on a cosmically short timescale. Read that again. Not eventually, over eons. A functioning planetary magnetic field, by the physics everyone accepted, required an off-axis wobble to keep itself alive at all. Saturn's field has no detectable tilt. None. Cassini's measurements, taken from closer to the planet than any instrument had ever gotten, showed the magnetic axis lined up with the rotation axis almost perfectly, so close to 0 degrees of difference that the deviation sits at or below the very limit of what Cassini's magnetometer could even measure. Think about what that means in practice. Imagine spinning a top with a magnet buried inside it, and no matter how precisely you measure the magnet's orientation, it points in exactly the same direction as the axis the top is spinning on. Not almost the same direction, not close enough to round off, but indistinguishable from perfectly aligned. By the dynamo theory that has explained magnetic fields on every other planet scientists have ever studied, that shouldn't be a physically stable situation. And yet, there Saturn sits, field intact, generating a magnetosphere large enough to influence the space around dozens of moons. This is not a small footnote in a data table. This is a planet quietly breaking one of the founding assumptions of an entire branch of planetary physics, and doing it in plain sight 10 years' worth of Cassini orbits deep into the mission before anyone got close enough to notice. Compare that to Earth, where the magnetic axis and the rotation axis are already off by roughly 11 degrees. Enough of a mismatch, according to standard dynamo theory, to keep our planet's field churning for billions of years. Jupiter's tilt is even larger. Every gas or rock planet scientists had ever measured before Cassini's final orbits showed some meaningful angle between the two axes, which is exactly why Saturn's near-perfect alignment reads less like a minor curiosity and more like a planet quietly failing a test every other world in the solar system has passed. Since that first mass measurement was published in 2019, researchers working through Cassini's remaining data have kept refining the picture rather than settling it. Studies published as recently as 2023, using measurements of micrometeoroid flux at Saturn and the fraction of non-icy pollutant material mixed into different parts of the ring system, have continued to converge on the same startling conclusion, not just that the rings are young, but that they are actively, measurably losing mass. Right now, raining material into Saturn's atmosphere fast enough that the entire ring system may not be a permanent feature of the solar system at all, but a temporary one, arriving late and destined to disappear again. What most people are not seeing in the beautiful photographs of Saturn's rings is that they are looking at something closer to a passing weather event on a geological timescale than a fixture as old as the planet itself. There's a very specific, already locked-in date on which scientists will get their next real-world chance to test everything Cassini found. Saturn's rings appear edge-on from Earth roughly once every 15 years, a consequence of the way the planet's 26.5-degree axial tilt lines up with its long 29.5-year orbit around the Sun. The most recent one occurred on March 23rd, 2025. The next will occur on October 15th, 2038, when the Sun's position relative to Saturn's ring plane flips from south to north, and the rings briefly vanish from view for observers on Earth. Historically, these crossings have been moments of genuine discovery. 13 of Saturn's moons were first spotted during past ring plane crossings, when the glare of the rings themselves stops drowning out fainter, smaller objects nearby. On October 15th, 2038, telescopes on Earth, and whatever spacecraft happen to be operating in the outer solar system by then, will get one more clean look at exactly the region Cassini sacrificed itself to study up close, a natural recurring experiment already scheduled by celestial mechanics that will let scientists check whether the ring rain and mass loss rates Cassini measured in 2017 are holding steady, accelerating, or doing something nobody has modeled yet. Now, the honest part. 2 specific things Cassini found in its final months remain genuinely unresolved, not settled facts dressed up as mysteries for dramatic effect. The magnetic field's near total lack of tilt still has no single confirmed explanation. The leading hypothesis, that deep layers of helium rain inside Saturn are smoothing out and hiding a real tilt from view, remains a model, not a measurement, because no instrument has ever gotten close enough to Saturn's actual interior to check it directly. And the age of the rings, while narrowed dramatically by Cassini's gravity data, still carries real uncertainty in exactly how they formed in the first place, whether from a shattered icy moon, a captured comet, or some other event entirely, a question the ring mass measurement alone cannot answer, because knowing how much material is there today doesn't by itself tell you how it arrived. Both puzzles point toward the same underlying honesty. Cassini didn't close these questions. It made them precise enough to finally be worth arguing about with real numbers instead of guesses. That distinction matters more than it sounds like it should. A vague mystery invites speculation, a precisely measured one, like a ring mass known down to a specific figure or a magnetic tilt pinned below a specific instrumental limit, invites testable competing models. which is a slower, less satisfying kind of progress than a clean answer, but a far more durable one. Step back, and there's a pattern here that goes well beyond one gas giant. Cassini was never approved, funded, or built to answer questions about magnetic dynamo theory or the age of planetary rings. Those weren't the headline goals in the original 1980s mission proposals. It was approved to study a planet, its moons, and its rings in general terms, using instruments designed with the knowledge available decades before launch. And yet, its most theory-shaking results came not from the years of careful, planned observation, but from the final, desperate improvisation of a spacecraft that was almost out of fuel, threading a gap nobody had ever crossed because engineers needed somewhere safe to send a dying probe. The most fundamental discovery about how Saturn's magnetic field actually behaves arrived as a byproduct of a decision made for planetary protection, not planetary science. This is not a rare irony in the history of exploration. It is closer to the rule. Voyager's most famous photograph, the pale blue dot, came from a camera that was about to be shut off forever. Some of the clearest evidence for water on Mars came from rovers built to look for something else entirely. Discovery, again and again, seems to arrive not on the schedule anyone wrote into a grant proposal, but at the exact moment resources run out and someone is forced to take one last, unplanned look. Think about what that means for how missions actually get approved in the first place. Nobody sits in front of a funding committee and asks for a spacecraft to run out of fuel on purpose near an untested gap between a planet and its rings. That plan only existed because 13 years of prior success had already been banked, giving engineers enough institutional trust to attempt something that risky with a mission everyone already considered a triumph. The safest thing Cassini's team could have done in 2017 was nothing at all. Let the spacecraft drift, declare victory, and shut it down quietly. Instead, the very last decision made about a 13-year-old space mission was also its most scientifically aggressive one, and it is difficult to imagine a clearer illustration of a simple, uncomfortable truth about how knowledge actually accumulates. The safest path rarely produces the discovery that rewrites the textbook. There's a detail from Cassini's very last hours that has stayed with the scientists who worked the mission. In the final images it sent back, hours before the plunge itself, Cassini captured the small moon Enceladus, slipping behind the enormous curve of Saturn, vanishing from the frame the way it always had, thousands of times before, except this was the last time any camera built by human hands would ever see it happen. Somewhere in that image is the exact spot where Cassini had discovered ice geysers erupting from a hidden ocean years earlier, proof, still sitting there in the dark, that Enceladus keeps whatever secrets it has regardless of who is watching. Then the antenna that took that picture turned itself forward one final time, not toward home, but toward the planet it was about to fall into, transmitting real data for exactly as long as its small thrusters could fight against a wind no spacecraft had ever flown into before until the atmosphere finally won, and a signal that had been traveling reliably across 1 billion miles for 20 years, simply quietly stopped. So here's everything in one breath. Cassini launched in 1997, spent 13 years studying Saturn up close, and in its final months threaded 22 unprecedented dives through the untested gap between the planet and its rings before deliberately plunging into Saturn's atmosphere on September 15, 2017 to protect the potentially life-bearing moons Enceladus and Titan from contamination. In its final passes, it found a magnetic field with no measurable tilt at all, defying nearly 40 years of dynamo theory. And it measured the ring's mass precisely enough to show they are likely only 10 to 100 million years old and actively losing material into Saturn right now. The next natural opportunity to check that ongoing ring rain against fresh observations arrives on October 15, 2038, and both the tilt and the exact origin of the rings remain genuinely open questions in 2026. If a spacecraft dying on purpose to protect the search for alien life and then breaking planetary physics on the way down is the kind of story you want more of, subscribe and turn notifications on, because I'll be covering what the 2038 ring plane crossing actually reveals the moment the data comes in. Here's the question for you. Does it make more sense to you that Saturn is hiding its tilt somewhere science hasn't reached yet, or that the dynamo theory itself needs to change? Let me know in the comments. I read every single one. Researchers studying the data were clear that something has to be hiding the tilt from Cassini's instruments, because the alternative, that Saturn's dynamo somehow works without one, would force a rewrite of physics that applies well beyond Saturn itself. One leading idea involves stable layers of helium rain, forming deep inside the planet and smoothing out the field's signature before it ever reaches the surface, effectively masking a tilt that might genuinely exist further down, out of reach of any spacecraft. But that explanation is a hypothesis, not a confirmed answer, and as of the most recent analyses of Cassini's magnetic field data, no single model has fully closed the case. Here is where this stops being an abstract puzzle about a gas giant 900 million miles away. Earth's own magnetic field is generated by exactly the same kind of process, a dynamo churning in our planet's molten outer core. And that field is the reason a hostile stream of solar radiation doesn't strip away our atmosphere the way it likely did to Mars billions of years ago. Every theoretical model scientists use to predict how long a planet's magnetic shield will last, on Earth or on any world orbiting any other star, rests on the same dynamo physics that Saturn's near-zero tilt appears to violate. If the underlying theory has a gap big enough for an entire planet to slip through, that gap doesn't stay confined to Saturn. It follows every calculation built on top of it, including the ones astronomers now use to guess which exoplanets might be shielded enough to hold onto water, air, and maybe life. Thousands of exoplanets have now been cataloged, and for almost every one of them, nobody can directly measure a magnetic field the way Cassini measured Saturn's. Instead, researchers lean on exactly the kind of dynamo models Saturn just complicated to estimate which distant worlds are even capable of holding on to a life-friendly atmosphere in the first place. Getting close enough to make that measurement in the first place very nearly didn't happen. The gap between Saturn's rings and its atmosphere had never been crossed by anything humans had built, and nobody could say with certainty what was actually inside it. Saturn's rings are made of ice and rock ranging from dust grains to boulders the size of houses, and mission engineers had no confirmed way of knowing whether the region just inside the ring's inner edge was genuinely as clear as models predicted, or whether it was seeded with debris fine enough to shred a spacecraft moving at tens of thousands of kilometers an hour. Here's where it gets worse. There was no way to test this safely first. The only way to find out whether the gap was survivable was to fly Cassini through it and see what happened on the other side. Nobody had flown anything through that gap before, which meant the models predicting it was safe were, by definition, untested. Ground-based radar had suggested the region was relatively clear of large debris, but relatively clear at a distance of nearly 1 billion miles is not the same as confirmed safe for a spacecraft moving at over 100,000 kilometers an hour, where even a grain of sand-sized particle could, in theory, cause serious damage on impact. The team had exactly one shot to get the first pass right, because a catastrophic failure on dive 1 would have ended the entire grand finale before it produced a single result. For the very first dive, on April 26, 2017, the team made a defensive choice that says everything about how seriously they took the risk. They oriented Cassini so its own large dish antenna faced forward into the direction of travel, using the spacecraft's most important piece of communications hardware as an improvised shield against anything it might hit. That decision came with a brutal trade-off. With the antenna pointed forward as a shield rather than back toward Earth, Cassini could not transmit anything during the crossing itself. For the better part of that first pass, mission control at JPL had absolutely no way of knowing whether their spacecraft was intact, damaged, or gone. Engineers who had spent years, in some cases decades, of their careers on this mission sat in a control room roughly 1 billion miles from the answer, watching a blank telemetry screen, waiting for a signal that either would or would not arrive. Sit with that for a second. The not knowing wasn't a dramatic embellishment added for a documentary. It was the actual, literal state of the mission for hours at a time, 22 separate times, each one a fresh roll of the dice with no way to intervene once the maneuver had begun. When the signal finally reappeared each time, it carried more than just confirmation that Cassini had survived. It carried something the mission had specifically been redesigned to capture: direct, close-up readings of the exact region between rings and planet that no instrument had ever sampled before. The gap turned out to be almost eerily empty, far less dusty than some models had feared, which is precisely why Cassini survived 22 passes without catastrophic damage. But almost empty is not the same as boring. Cassini's ion and neutral mass spectrometer, built to sample gas composition, picked up something researchers were not expecting at all: material raining down out of the rings themselves, falling into Saturn's upper atmosphere in a phenomenon scientists had already nicknamed ring rain, based on earlier ground-based infrared observations. What Cassini found up close, though, didn't match the simple picture. The rain wasn't just water ice, the obvious guess given what the rings are made of. It included methane and heavier organic molecules, mixed with what appeared to be carbon monoxide, a chemical signature that does not have an agreed-upon origin, and which, some researchers have speculated, could be a leftover trace of an ancient comet impact deep in the ring's history. That story, in the mission scientists' own words at the time, was still evolving, even as Cassini burned up in the atmosphere it was busy sampling. Even the very last moments of the plunge itself are still being pored over. Because Saturn sits so far from Earth, Cassini's final signal took about 83 minutes to cross the gap and reach NASA's Deep Space Network dish in Canberra, Australia. meaning that by the time controllers on Earth watched the telemetry go flat, the spacecraft itself had already been gone for well over an hour. In the roughly 90 seconds between entering Saturn's upper atmosphere and losing its ability to keep its antenna pointed at Earth, Cassini's instruments recorded the composition of the gas around it, the temperature, and the structure of the magnetic field in a region no probe had ever physically touched before disintegrating. That final descent data, gathered while the spacecraft was actively tumbling and burning, is still being cross-checked against models of Saturn's upper atmosphere nearly a decade later. Here's what is happening right now in 2026, nearly 9 years after Cassini's final transmission. The gravity data collected during those same 22 dives, precise measurements of how Saturn's gravity tugged on Cassini's velocity, accurate down to a fraction of a millimeter per second, has been used to calculate something scientists had argued about for decades, the actual mass of Saturn's rings. The number that came back, published in the journal Science by lead researcher Luciano Yes and colleagues, was startlingly small. About 1.54 times 10 to the 19th kilograms, roughly 15 sextillion kilograms, or a little under half the mass of Saturn's small moon Mimas. That number matters because ring mass and ring age are directly linked. Rings built mostly of bright, reflective ice darken steadily over time as micrometeoroids rain dust and debris onto them, and a low mass means there simply hasn't been enough material accumulating for very long. The resulting estimate, Saturn's rings are somewhere between 10 million and 100 million years old, meaning translated into a scale you can actually picture. Dinosaurs were already walking the Earth for tens of millions of years before Saturn had rings at all. A planet 4.5 billion years old, wearing an ornament that might be less than 1/40th that age.